So the person doing the presentation here on Passive House is Bjornson. He's making his way up. And I horned in because I wanted to introduce them. And the reason I wanted to introduce this is it just happens that I went to one of the houses they're working on near Gimli. It's retirement homes being built from scratch. And they'll tell you all about the technology. But what really struck me was how beautiful it was. The technology has an aesthetic effect. It's sometimes obvious and sometimes not. It will be, aside from being incredibly comfortable and incredibly inexpensive to live in, it'll be a beautiful home to live in too. Eric.
My name is Eric Bjornson, and I founded a company called Sundail Building Performance in 2002 with a partner, and we grew the company over the last 12 to 13 years, doing mainly retrofitting. So we would take old buildings, both mainly houses, and do insulation retrofits. So looking at turn-of-the-century homes, usually up to about 1940 or 50, and upgrading attic insulation, upgrading basement insulation, upgrading wall insulation. And it's been good and it's been satisfying, but at the same time it's been a little bit frustrating to see all these houses that we're upgrading and making them slightly better, not great, but marginally better. And at the same time, there's houses being built that are not much better than the houses that we're retrofitting. And so we've done this for 10 years and figure, okay, we gotta try to figure out what's the best way that we should be building right now. Rather than complaining about it, maybe we can try to figure out a better way to build. And so kind of went down the path of saying, okay, we're gonna start looking at new construction options. What's perhaps the smartest way to build? And got introduced to the Passive House standard, which is not the only good standard and the only way to build a good house, but it seemed like a really good guideline for reaching really a very high level of efficiency and kind of giving some guidance and kind of a structure to follow, and also helped with identifying with that in terms of just having a marketable differentiation where people are starting to know the name Passive House. So I want to take a bit of time today to talk about the Passive House standard, what it is, and show you some examples from a house that's soon to be Manitoba's first certified Passive House, and show you about what it took to reach that standard here in Manitoba. So we're going to talk about what the Passive House standard is, designing to achieve the standard, and then show some examples of how we achieved that standard at this home here. So it's a building standard. It's basically kind of a set of rules that you have to follow if you want to meet that standard. Comes kind of based in Germany, and it's really well accepted, I guess, in a lot of European countries, and only just starting to get some attention here. And so it's a kind of a proven model, so it's been done many, many times before, so it's something that organizations can reference, and it's quantifiable. So if your house meets a Passive House standard, you know certain things about that house. You know how much energy it's going to use based on its size. You know it's going to have some comfort measures that are going to ensure a high level of comfort and high level of indoor air quality. And so it's verified. So if you have a house that is a certified Passive House, then a third party has looked at how it was designed and how it was built and verifies that it did meet the standard. And so the primary kind of metric, I guess, to meet that standard is limiting the amount of energy used for heating. So there's a set amount of energy that a Passive House building can use for a given floor area. That's pretty much what it is, and it's a very, very challenging standard, particularly in such a cold climate like ours. And we'll talk more about what exactly that quantity of heat is. And so it doesn't specify how you have to build, or what materials you use, or what equipment you use. It basically sets the standard in terms of how much energy it can use, and then it's up to the designer to determine the best way to build it. So for different climates and for different local building materials and local construction practices. And so some key aspects, which I'll talk more about, make energy efficient use of the sun, make good use of the internal heat sources that are already being used for other reasons, high rates of heat recovery from the ventilation, And a lot of these basically render the conventional heating system unnecessary. And so that's maybe where the term passive house comes from. In some ways it's a bit of a misnomer because there still is some active systems in a passive house, but there typically would not be a natural gas furnace that we're used to seeing in our homes. And so a side effect, it's kind of based on energy efficiency, but a side effect is high levels of comfort, high levels of usually increased durability, and much better air quality than would be typical. And so just comparing this to some other words that kind of surround this idea. So looking at net zero, net positive, and off-grid. And so they're all different, but most of them would probably start with something that resembles a passive house building. So looking first at the building shell and reducing the demand as much as possible. And then to go from a passive house to a net zero, you'd be adding renewables. So you'd be adding probably some photovoltaic and then having a net metering so that over the course of a year, you've produced as much energy as you've consumed. Net positive, very much the same thing, except you're just adding more site generation, so you're producing more than you're consuming. And then off-grid. So again, you probably want to start with a building that meets or comes close to meeting the passive house standard, and then you'd have site generation and likely site storage. So this is the kind of the nuts and bolts in terms of what you need to do to meet the standard. So for heating, 15 kilowatt hours per square meter per year. For a given square meter floor area in your building, it can use no more than 15 kilowatt hours in a year. And so that makes sense to me because I've been looking at this for the last 2 years, but to make sense of that for kind of an average home, 1,400 square foot home, which is what we're just building, it's going to use a total of, actually I'll break that down to just a cost. At 8 cents cost per kilowatt hour, today's rate, about $150 worth of electricity to heat that home for an entire year. So very, very low amounts of energy input for space heating. And primary energy, basically the total amount of energy used by the entire building for not just space heating, but domestic hot water, ventilation, just the general electrical use within the home, can't exceed 120 kilowatt hours per square meter per year. Air tightness, they've specified an air tightness, basically it's more or less required in order to meet that heating demand standard. And it's also related to building durability, but the standard that's specified is 0.6 air changes per hour at 50 pascals. That's measured with a blower door, and that's basically controlling the amount of, or reducing the amount of uncontrolled air exchange between the inside and outside. So making sure that your walls really do seal you off from the exterior. And feel free to jump in with questions. If someone has something just to clarify, feel free to jump in. Yeah, that didn't take long. Yeah, so that you're not really concerned with, but in order to get air exchange, you need an inlet and an outlet. So if you had a door open on one side and a window on the other, you're definitely going to get a lot of air exchange. But if you're just opening a door, coming in and closing the door, it's actually going to be very little air moving through that. And you can actually see it if you go to a house that has a very high degree of air tightness on a cooler day. You can open the door and leave it open, provided all the windows are closed, and it's almost like an invisible line where you walk in and it's conditioned temperatures, and you walk back out and it's cold. Even though the door is not closed, it's almost like there's a wall there. So continuous ventilation, so that's specified in the standard, so you need to have your ventilation system running 100% of the time. So there's always fresh air being brought into the building, and it's being distributed to every occupied room in the house. So talk a little bit more about how that looks. But it's specified approximately, depending on the size of the building and the number of people that are in it, about 30 cubic meters per hour per person, which is basically kind of a accepted amount of quality ventilation to maintain health and comfort. So this is a little bit lower down on maybe the focus of the standard, but it's there. So, and as a designer, it's very important. So surface temperature of the windows, and really all the surfaces on the interior of the house, but the windows are going to be the most challenging. There's a comfort criteria and a hygiene criteria. So the comfort criteria says that our bodies are uncomfortable if one side of our body is exposed to a temperature, one temperature, and then the other side of our body is exposed to a cooler or warmer temperature. So we want to be kind of in a room with standard temperatures, I guess, throughout, without any cold surfaces. So wanting to make sure that the surface of the windows is not cold, so that if you're standing next to a window, you don't feel uncomfortable. And then hygiene criteria. So in this climate, the comfort criteria is going to be the more challenging one to meet. So we're trying to keep the coldest surface in the building no colder than 4 degrees, or no more than 4 degrees colder than the air temperature. So that's a pretty big challenge when we have, minus 40 on the other side of that window. And then hygiene criteria, and that's really making sure that there's no surfaces in the building that are cold enough to promote mold growth. So moisture activity, which could result in mold growth. It's important to look at, but probably if you've met the comfort criteria, you've met this hygiene criteria. And then summer overheating. So there's usually most of the heating provided to the building is going to be provided through south-facing glass windows. So that's great, but you've got to make sure that having all that south-facing glass or glass in the building is not going to cause overheating. So there's built into the standard, no more than 10% of the time can the indoor air temperature, or could the design of the building result in an indoor air temperature above 25 degrees Celsius. And so this is all figured out before the building is built using a software called PHPP, and it's a Goliath of a spreadsheet. And I'm, it's something that I, don't like to do personally, but you can have others do it for you to get you going, and then you can tweak it. And this is what takes all of the ways in which the building loses heat, calculates that, takes all the ways in which the building gains heat, and creates an energy balance. So we can see here on the left, that column on the left is showing all the ways in which the building loses heat, and on the right is showing all the ways in which the building makes up that heat to maintain an indoor air temperature of around 20 Celsius. So on the left, we've got, I'll just go through it quickly. At the top there, that white box, 16.3 kilowatt hours of 90 kilowatt hours total. So we're talking almost percentage-wise, we could almost look at it that way. Non-useful heat gains, that's kind of an overheating scenario, so that's heat that's being created that we don't really need. Below that is the heat that is being lost through the exterior walls, so 17/90, so almost 20% of the heat is going through the exterior walls, 7% through the roof, 10% through the floor, 32% through the windows, so the windows are by far the biggest cost in terms of heat loss. And exterior door, small amount through the exterior door because there's only one of them. And then ventilation, so we're using an extremely efficient heat recovery ventilator. So only maybe 6 or 7% of our heat loss is going through our exhaust airstream of the HRV. And it's running 100% of the time, so that's incredible how much heat it's able to recover. And so that's the losses, and now we look at the gains. And so 60/90, so about 66% of the gain on this particular passive house is coming from the windows. So even though they're the biggest loss, they more than make up for it on the gain side. And so that's looking at using the right type of glass, but most importantly, putting the windows on the right side of the house and making sure they're not shaded. So some sites, that's going to be a lot easier than others. In this particular site, it was really on an open acreage, so there was no shading issues, and we could point the building straight south. Internal heat gains, so that's the one box there below. So that is the people in the building, that's appliances running, the TV running, basically all of the heat that's generated in the building for other reasons. And then heating demand, that's the red one. So that's the portion that is created by the heating system. So a very, very small amount created by the heating system. Electric resistance in this case. We're talking maybe 15% of the heat is actually being created by your heater. And then that 4.6, that's kind of a calculation correction number. So it's not worth, it doesn't make a part of that. So that's now just talking about how to get there. And so early planning is important. And so this could be even in the, kind of the neighborhood development stage, where these two things I'm going to talk about. So form factor, but maybe before that even is orientation. So making sure that you can orient the building for solar gain, and so trying as much as you can to point the building south. And so that could mean how streets are aligned. It could mean how basically buildings are aligned in the community. It can also mean before you, so you may not have any choice on that, but you have your building lot. But then it's around picking how to orient your building and pick which rooms are going where. And then shape factor. So as a builder, we will often get a project. There might already be plans done or close to getting plans. But so if I can say two things before you start drawing your plans is try to get the orientation right and try to pay attention to shape factor as much as you can. And what that is reducing your surface area, your heat loss surface area, walls, roof, and floor, as a ratio of your floor area. So the more, get rid of the cooling fins, basically. So not to say it has to look like a box, but more or less, the more it looks like a box, the more efficient it's going to be. And there's many different ways to make something that is kind of boxy in design look either less like a box or still quite beautiful. And so there's many different ways to do the optimization for solar gain. So we have to look at two things. We have to look at maximizing solar gain, but minimizing overheating. So this is looking at probably shading south-facing windows. Probably most people in this room know about how window shades work great in our geography, just because the sun is low in the sky in the winter and it's high in the sky in the summer. So we can have basically a overhang or a louver or a shading device that just works. So this is just using Google SketchUp. So we have this house and we can actually set the geography of where the building is, and we can set the time of day and we can set the time of year. And so this is today at 3 o'clock, pretty much right now. That's what this building is going to look like in terms of where the shading is going to be against those south-facing windows. You can look at it December 21st at 3 p.m. So we've got full solar exposure to those south windows, bringing in piles of heat. And then looking July 1st at 3 p.m. So they're almost entirely shaded. So it's a time where you probably don't want a whole lot of solar gain. And so the shading works great. Everyone saw that? And so that's just an example. That's the home built, and we can see the shadow line, and it corresponds really well to what the models showed. And so there's the Passive House Planning Package, which is the Goliath spreadsheet, which I'm not a huge fan of, but there's also a SketchUp version to allow you to do a lot of the hard work. If you prefer to draw the house as opposed to type numbers in a spreadsheet, then this is the way to do it. So this allows you to do energy modeling, not every single line item, but just about using a drawing software. So you draw the building, you assign different assemblies to different faces on the building, and it will do a energy model right inside of SketchUp. And it'll also look at shading. So the shading calculation for PHPP, which is that spreadsheet, is a cumbersome process, but this will take all of the numbers and basically plug them into that spreadsheet for you. So now that we figured out what the layout of the building is going to look like, and we figured out maybe where windows are going to go, now we're looking at all of the building details, so all of the connections, where the walls meet the roof and where the roof meets the floor, where the windows are installed, where the doors are installed, anything that's penetrating the envelope. And we want to make sure it's a thermal bridge-free design. And so we may have a super insulated shell for the most part, but if we have a number of areas where there's basically just a highway to take heat from inside to outside, it's a major penalty, and by eliminating those, we can actually kind of reduce the amount of insulation that we're using over the entire surface. So that's just a couple examples, and there's usually dozens of details in any given house. So I'm just put a couple examples here of things that maybe don't get much attention paid to them. So this is a form that we had cut for concrete strip footing. So that's an area that usually does not get insulated, so where the footing is in contact with the ground, that's a thermal bridge. So this is basically putting insulation, high compressive strength, high density EPS foam underneath the footing. And so that's basically a tray that was made, so that'll have concrete poured in it, and then there was going to be a grate being poured on top of that. So another example, this is ducting. It's a foam ducting. And so whenever there's going to be a pipe penetrating the envelope, so an HRV is going to have two, one intake, one exhaust. So that's a really nice solution to avoid having a thermal bridge through there, as opposed to, say, using a metal duct, or even a plastic duct is not going to be as have such a low transmission as this will. Here, pass that around, feel free. Windows, so it's important to have a high quality window and a window frame and window glass, but the installation can make a huge difference and can turn what could have been a great kind of a opening into a major kind of a energy conduit from inside to outside. Window sill is probably one of the more difficult ones to figure out. Window jambs and headers, still difficult, but maybe not quite as difficult, so definitely want to pay attention there, and not just from a heat loss perspective, but probably even more importantly from a building durability perspective, because that's probably where water is going to get into your building assembly, and so wanting to make sure that that doesn't happen, because if the building doesn't last, then it doesn't really matter. And so thermal bridge analysis is done in for the most part, in a free program called Therm. So where you can basically draw out the building assembly. Again, maybe not for everybody, but there's consultants that do this regularly. And so you can have your building assembly and you can optimize it to make sure that it's as thermal bridge free as possible, and eliminate, kind of have a threshold for things that you won't accept. So air tightness. So this is probably one of the biggest deviations from conventional construction that we're used to, that we used in this passive house, and that's quite commonly used in passive houses. And that's the way we achieve airtight construction. So there's no polyethylene vapor barrier. Instead of using that, we used rigid vapor barrier, in this case plywood. So the plywood was both the structural sheeting and was the air vapor barrier. And so we want to make sure we use a good quality of plywood, and then we're using air sealing tapes and gaskets to look at wherever there's a seam in the plywood to seal that off, and that's how we achieve a very airtight shell in this case. And so I brought some pieces of this tape. So this is a specialty tape designed for that purpose. It's not very common to see here, but it's common in other areas. So you can feel free to pass that around, and if you really want to, feel free to keep a piece. In terms of, so its perm rating is a little bit higher than poly would be, but perm rating, and it's important to have kind of a threshold in terms of perm rating, but it's not important to be as high as poly is. The most important part is to avoid the actual air bypass from the air vapor barrier. So you could have I'd rather have this with almost no air leakage than have poly with a modest amount of air leakage. Not only that, but it's not poly, it's a lot easier to do, and it's durable. So if someone's going to put a hole in this, they know they're putting a hole in it. If someone's putting a hole in poly during a renovation or electrical upgrade, very difficult to maintain it. I think to achieve this level of air tightness, it's actually quicker. So it's a lot easier to work with plywood. There's many reasons, but that's one of the biggest ones. It's a lot easier just to have confidence that when we're done, it's airtight, because you can actually see it. You put the plywood up and you put the tape up and you know it's airtight. Where with the poly, you might have different layers folding onto each other, and they just might not seal. Durability too, so if it's good when we're done with it, it's probably going to stay that way for quite a long time. It's not going to be coming apart, and it's not using plastic, which is kind of nice too. So that's the ceiling. So in this case, on the ceiling in this particular house, it served three purposes, that plywood. So it was the structural sheeting, it was the air vapor barrier, and it was the finished ceiling. So it ended up not getting drywall. We just put strips of rough sawn fir over top of the tape, and then that ended up being the exposed wood ceiling in this house. And so it works. So we did a blower door test on this before we put drywall on. So the windows were in, everything was done in terms of the shell. Blower door test, so maybe a typical house might test, you're basically testing the air leakage rate of the house. Probably most people here have seen a blower door, depressurize the house and then measure how much airflow it takes to hold the house at a 50 Pascal pressure difference between inside and outside. And so maybe typical would show that you might have, say, maybe 2 or 3 or 4 air changes per hour at that pressure difference. And so Passive House sets a standard at 0.6 air changes per hour. So this house here, we had 0.26 air changes per hour. So about, half as much leakage as the Passive House standard is, which we were quite happy with. And we didn't go through extensive effort. We basically just followed the procedure that we put together, and that's where we landed. And so insulating. So we, maybe there's some ideology here, but we like to use cellulose insulation. It's renewable, it's made in Manitoba, it's a recycled product. And so we basically designed a system so that we can get a very high, it's also lowest cost per R value, maybe especially if you ignore labor. So we have basically a web truss. We built a truss system for the floor, the walls, and the roof. Basically a cavity that has very little wood going from the inside to the outside, and then we pack that tightly with cellulose insulation. So this picture is looking into the floor system, and so we're just looking through the wood web floor trusses. You can see on the right-hand side, we've got that cavity with a mesh on it. And that's just to segregate the cavities so we can kind of focus on packing insulation one cavity at a time, and get it packed in really tightly so that we're not worried about settling. So that's the walls going up. Again, we used, this was probably one of the more unique aspects of this project. So we used a wood web truss for the walls. So as opposed to a double stud construction or a handmade Larson truss construction, we used a wood web truss. Basically had a truss fabricator build these for us. We had an engineer tell us that this would work in terms of structure, and then we put the wall up with these trusses. And so then to clad the, kind of making a sandwich, so the inside is plywood, and then we've got this truss to create the cavity, and then the outside we need to retain the cellulose somehow and have an air barrier. So in this case we used a membrane called Mento Plus. It's a high permeability and really strong membrane that we stapled on. And then used battens to hold it, sandwich it against the structure, and then we packed that cavity tight with cellulose insulation. I think the next project we're going to use, it's a sheet good. It's called Agipan. It's basically a vapor permeable fiberboard. Also has a very high perm rating, but it's rigid, so we're not going to get the issue with bowing. And we're also looking at modular production, so it'll be much more conducive to shipping modules with a rigid exterior as opposed to a membrane. And then packing in the cellulose. So that's a kind of a procedure that you need a lot of patience for to get that density. So you're looking to achieve a certain amount of cellulose in a certain volume. 3.5 pounds per cubic foot is kind of the number that has been calculated that will prevent settling. So you want to basically monitor it to make sure you are achieving that, and it really involves using a lot of time. So you have a very high air ratio to material ratio to get that material to pack in very tightly. So it takes a pile of patience, and you have to trust the person that's doing it, that they're going to be patient and take whatever time it takes. So mechanical ventilation and space heating. Passive House has fresh air brought to every single living room. So the bedrooms, the living room are all going to have their own dedicated vent, providing fresh air to each room. And what's unique about the air distribution system in a typical Passive House is there's not going to be any recirculation. So all of the air that's coming out of that vent is 100% outdoor fresh air. It comes in, it gets, the heat gets transferred to it from the exhaust airstream, and then it gets distributed to the rooms. Probably getting topped up in the colder times of the year with a little bit of additional heat. And so we have to design room by room based on room size, and the type of room it is will determine how much airflow goes to each room. And then we'll have our exhaust rooms will be from the kitchen, the bathroom, and in this case there was kind of an exercise room that we exhausted from. And so this is what we used for a mechanical system design. So we've got a HRV, we used a Zender unit, comes from Europe. Hopefully there'll be local manufacturers that make very high quality HRVs here soon. We've got a post heater, so up at the top of that HRV, that's a heater that's adding a little bit of additional heat to the air being supplied to the rooms. And then we've got a preheater, which is kind of a concept that is really helpful for increasing the efficiency of the HRV in very cold climates. And so what that's doing is it's grabbing some heat from the ground. There's a little miniature geothermal loop in the ground, and it's using a pump to just cycle the fluid from that loop through that coil to bring the air temperature up to something maybe around 0, 1, or 2 Celsius before it gets to the HRV. And that's preventing the HRV from going into a defrost mode. Because when a HRV goes into defrost mode, no matter how efficient it was before, its efficiency almost drops to 0. Or maybe, yeah, probably does drop to 0. So that's basically avoiding that scenario, which happens for a great portion of the time in a cold climate. And so that's it installed. That little light colored box there, that's just a filter to filter the air before it gets to that heat exchanger. And that's our entire mechanical room. So the entire mechanical room for this house is in a space about 6 by 4 feet. That includes the water softener and the pressure tank, the hot water tank, the HRV, everything in a tiny room like that. So that's kind of nice. There's very little maintenance. Really all the maintenance that should be involved is changing the filters or cleaning the filters on the HRV and that filter before the preheater. And so something we did unique here, so we had this, built this house, we suggested it to the designer, Bridgman Collaborative Architecture did the design on this building, and they did the initial, or the energy modeling. But we suggested, there was talk about doing solar thermal, and there was talk about heat pumps, and so we looked at them, and they didn't seem to be economic in terms of cutting the use further, but we figured it might have been smart to put in kind of a solar-ready hot water tank. So this hot water tank has integrated heat exchangers, and so the top heat exchanger is used to extract heat from the tank, and the bottom heat exchanger is used to add heat to the tank. And so we don't have anything connected to the bottom heat exchanger. That might be for future solar thermal or future heat pump, but the top, we're extracting all of the heat being used for the space heating from the top of that tank. So as opposed to using an electric resistance heater, we're pulling it out of the tank so that if solar thermal is added in the future, it's already providing heat for domestic hot water and space heating. That's the tank there. And so we did something, a little bit of a creative solution for meeting the comfort criteria at the windows. So in order to not have that cooler surface temperature of the window in this climate, you would have to have a window that I don't even think has been invented yet. It would probably be a quad pane or a 5-pane window. It would probably cost an absolute fortune. So we've got kind of the best available windows we could find locally. And then we, to meet the standard, 5 minutes. We had to put some type of a heating element near the windows so that on cold days of the year, people standing or sitting near the windows weren't going to feel that chill off the window. So there was already a deep sill, and there was already planned to put like a kind of a decorative sill there. So we suggested limestone, and then we had the Gillis quarries. They cut these grooves in the limestone for us. So then we put some 3/8-inch hydronic tubing, and we ran that it basically has a hydronic loop, so these windowsills are actually little radiators. We're going to turn them on next week. I hope it works. And so yeah, this is just another kind of a minor feature. So it's not a requirement for a passive house, but I think it's just a nice idea. So home run piping for domestic hot water distribution. And so there's maybe 2 advantages. So one, we have a lot of the piping, or some of the piping running through our floor, which is kind of the insulation layer. So we definitely did not ever want to have a leak there. So what this does is it runs a dedicated line from your hot water tank through a distribution manifold to every fixture. So a dedicated line all the way to your bathroom sink, kitchen sink, shower, toilet, everything's got its own dedicated line. So no fittings throughout the entire length. And so that's one advantage, no fitting, so it's really easy to install. You run a line here, you fish the line through, and you're done. But the other advantage is you have less hot water left in the pipe. So particularly, say for a kitchen sink, you might have one dish to wash, or you might want to wash your hands. So instead of waiting there for 2 minutes and using it for 20 seconds of hot water, you might be waiting for only 45 seconds to do your thing. So you're not wasting all of that. We're not wasting the water for one, and you're also not leaving that heated water in the pipes to cool after you walk away from the sink. And so for the most part we used 1/2 inch because the runs were relatively short, but we had one kitchen sink run, so you can see this red line here. We downgraded that to 3/8 inch line so that it's less water in the pipe. And we have another line going to a dishwasher right beside it at 1/2 inch, so if we find that there's too much of a pressure drop and they need more volume, we can switch it off and share with the dishwasher, but we're going to try that out just to try to allow you to get hot water to the tap quite quickly. Yeah, so this is a house that's just about finished right now. It's going to be hopefully Manitoba's first certified passive house. Hopefully that's going to happen in June. We're going to be having a tour of it May 6th and 7th, one organized tour on May 6th and an open house on May 7th. If anyone's interested in seeing it, I could send an invitation. I have a kind of a sign-up paper at the booth there. We're happy to have you there.
Where is it?
It's in Sandy Hook, Manitoba. Yeah, near Gimli. It could. No, there's a passive house complex being done in Saskatoon right now, and it does have a basement. It typically would have, we don't consider our basements generally as conditioned space. They're kind of utility space, so that would be make it difficult to achieve passive house. But if the basement was designed as conditioned space, like usable living area, maybe it might be a touch higher out of the ground to allow windows. It would work just fine. It's tough to quantify because this was our first one, so we put in a lot more time because we were figuring a lot of the things out as we went. But there's going to be some that are unavoidable, so there's additional time on detailing and air sealing that you're probably not going to spend on a house that's that you're not caring so much about the efficiency. Tough to quantify. Yeah, it's tough again because I don't know what this house would have cost as a conventional build necessarily. I think the way this one's, when it's complete, we're probably going to be around $300 a square foot, but that's pretty nicely finished, like really high-end cabinets, high-end flooring. But yeah, that's probably where we'll end. So certainly there's a premium, but it's not outrageous.